Okay, we're recording, we're sending. Okay, that's good. Chapter 9, that's where we're at, huh? We have a request for chapter 6 or chapter 9, number 6 and number 8. And I think number 7, 6, 7, and 8 also, I suppose. But what I'm going to do is I'm going to show you essentially, pretty much all of these problems are the same. 6, 7, 8, and even 4 and 5. Excuse me. All of these problems are really the same problem. And so we will look at one of them and show you how to solve it. Then you can use that to solve all the rest of them. I think probably number probably number 6 is the best one to do with the wheelbarrow. So the way that these problems are done. Hold on a second, let me share my screen with everybody. So the way that these problems with torque are done is a little bit different than the problems with forces because you have an extra equation. When we're doing forces, you would take all the forces that are in the x direction, all the ones that are in the x direction. In this problem, there are no forces left and right. There's only forces up and down. So you wouldn't have to do any forces in the x direction, but then we would look at the forces in the y direction. And if we would add them together, so this one would be a positive force plus a negative force added together. And then there's also a force in here that they don't mention, that is the normal force on the tire with the ground, and because there's the weight of this, but there's also a normal force pushing up on the tire here. So you might add all three of those forces together and then say, is there any acceleration? Because if you add all your forces together, it has to equal mass times acceleration. There is no acceleration. And so these three forces, this one, and the normal force on the wheel would be adding to 0. So that would give you one equation to solve. But usually when you have these forces that are not lined up with each other, this one's over here, this one's here, and this one's here, you have to deal with the torques. And so you have to have the torque equation, and the torque equation says, that the sum of the torques is equal to 0 if there's no rotation, if there's no angular acceleration. And that's where we get to in these kinds of problems, is that adding all of the torques together to equal 0 for that third static equilibrium condition. Now, when you're adding torques together, you have to choose a point where you're going to measure distances from. Usually we choose the point about which things rotate, which is, in this case, right at the axle of his wheel. And then you have forces times distances times the angle between the distance and force vectors. So from the center to this first force, here is our distance vector. It goes right along the handle because the force acts on the handle. And there's an angle here, and they tell us the angle. The center of the mass, so the 1.585 meter long handle is making an angle of 23 degrees above the horizontal. So here is the horizontal. Here is that angle right there. That's 23 degrees above that, right? So the angle between this force and this handle is 90 degrees plus the 23 degrees. So this would be force. The force is the lifting force. The distance is the length of the handle times the, is it sine? I think it's sine with the torque, times the sine of that angle, 90 plus 23. Then the wheelbarrow has this mass in it of 105 kilograms of soil. And the center of mass is 1.15 meters from the wheel. So it's right here. Right? So you've got this 1.15, or sorry, 105 kilometer, 105 kilogram mass at 1.15 meters away from here, right? So there's another force and another distance. The only real challenge there is to figure out that angle, because that angle is not given, I don't believe, in this problem. Right, that angle is not given. So that becomes a little bit of a challenge. We have to figure what that is. And that we can find by doing a little bit of geometry, essentially. So we know that the handle makes this 23-degree angle with the handle and the horizontal here. And we're looking for this remaining angle here. What is the rest of that angle? I'm trying to remember how we did that. I'm pretty sure I had to draw a different picture to make sense of that. Let's go draw another picture really quick. So this is the point of our wheel on our wheelbarrow. Come up here, we have our angle theta here. And then we have this other force that comes up from here. And we know the distance here. Excuse me. We know this distance here. Oh, I know. Oh, this 1.15 meters is not this distance from here to here. The 1.15 meters is the distance from here to here. So that should say the center of mass is 1.15 meters horizontally from the wheel. I'm pretty sure that's correct. Check. Let's see. Let me just check the code to make sure that's correct. That is not correct. Somebody changed this. So I'm going to do the math in my head real quick. Yeah, they're missing something in this one. I think I rewrote this problem, but I didn't save it to this particular homework set because this should have a sine theta right here. This should be divided by d2 times sine theta. Chapter 6. 1 meter from the wheel, 1.5 center mass, and 1.6 meter from the wheel, 1.7 upwards. So the way that they've actually solved this problem, the distances are all horizontal distances, but the way that it should be solved, it should be at the angle. I'm going to fix that question and come back to it. I have to fix the code on that one. Let's do this one here, because I know this one is correct. All right, so this one is the same kind of idea. We have forces that are horizontal, we have forces that are vertical, none that are horizontal. So we don't have any x forces, just y forces. And you have essentially two equations you can build. You can build your first set of equations from let's do this. You build your first set of equations from the horizontal. You have forces from this can that are the weight of the can down. Just mass of can times gravity. Then somewhere in the middle of the board, right in the middle of the board, you have the weight of the board. Wherever the middle of the board is, it should be somewhere, over the cliff so that it doesn't tip over. And then somewhere you have the weight of the cat. Somewhere out here you're going to have the weight of the cat. And that's the thing you don't know. We don't know where the cat is. We know the weight of the cat. We just don't know where the weight of the kid. We'll call it. So it's a different C instead of a K instead of C. This equation here won't do you really any good though, because all it's going to do is it's going to show you that, and actually, there's actually one more force in here, and that's the normal force pressing up on the board. And the normal force would act, you actually have another, you have a normal force essentially acting up at the weight of the board and one acting up here. But this isn't going to tell you anything. It's just going to tell you that the normal force equals all these forces, and that's fine. However, each one of these forces exerts a torque on the board. It creates a torque. So the weight of the can exerts a torque, and if we measure all of our torques from this point right here, right at the cliff face here, then we're good. We have the weight of the can. We know the distance to the can. We know the distance to the can is whatever they tell you. We know the distance to the center of the board, which is this way over here, distance to the board, or we could call this R, C, and R, B like they do in the book. But we don't know the distance here to the cat. That's the one that we want to actually calculate, the distance to the kitty, R kitty. So what does it look like when you set up an equation like this with torques? First of all, you have to assign a direction for each of the torques. Torques that cause a counterclockwise direction will be positive. So the torque from the can, this is a tau by the way, not a T. The torque from the can is going to be counterclockwise, so that will be positive. The torque from the cat will cause this thing to rotate counterclockwise. It's going to cause this board to rotate downward on this end. So the torque from the kitty is also going to be counterclockwise, and it's also going to be a positive torque, counterclockwise. So that'll be positive. However, the weight of the board is trying to rotate this thing clockwise. So that's going to be a negative one. And this is the stuff that's most important. You got to make sure we get those correct. So we're going to essentially have the torque from the can plus the torque from the kitty. Those are two positive ones. That's why they have their positives in front of them. Minus the torque from the weight of the board has to equal 0 if it's not going to rotate. Now, how do we plug everything in? All these forces are 90 degrees, so we don't have to worry about angles. Sine of 90 degrees is just 1. But each torque has a distance times a force. The distance to the cat times the force of the cat. The distance to the cat is whatever distance they tell you. Or the can, rather, not the cat. And then the force of the can is the weight of the can. And that's the mass of the can times gravity. And then the torque from the kitty is the distance to the kitty, which we don't know. That's the thing we're going to solve for. So we're going to just write that in we're going to write that in as a variable. We'll call it R to the kitty, or whatever we're going to call it. And then the force that the kitty causes is the weight of the kitty, which is the mass of the kitty, times gravity. And then the torque from the board is, we're going to put a minus in front of that, and it's going to be the distance to the center of mass of the board, whatever that is. And they tell you that too, the distance to the center of the mass of the board, times the mass of the board, times gravity. And that all has to equal 0. And then you can solve it for the one thing you don't know, which is the R, the distance to the kitty cat. And this is the same way you do the one on the painter. Except on the painter, you don't know how far he is from one side or the other or something like that. Let me give you a clue. With the one on the painter, you'll be tempted, it may be easier to set your rotational point at one end or the other. Doesn't matter if the board actually rotates. But whatever one you set it at, it's going to want to know the distance from one side or the other. So you're going to have to maybe do some calculations at the end. You might be calculating the distance from one side and it wants to know the distance from the other side. So you have to keep it in mind. But this is almost always the kind of equation you're going to get to solve when you're doing torque problems. Some torques added, some torques subtracted equaling 0, you're done, kind of thing.
So how do we rearrange it to equal 1? Okay.
Subtract this one, add this one, divide by m, k, and g. So that's true for this number, whatever number this one is, 6 or 7 or whatever, 7. It's true for 8. Um, 5 definitely different because you have some different torques at different angles, but they give you both of these angles. And so you instead of having so this force would cause a counterclockwise. That one would be positive. This one would be negative. And then you measure it from the bottom of the pole, and you're going to get an angle. So this one's going to be a force times a distance times an angle. This one's going to, and the distance is along here. Force times a distance and an angle times the sine of an angle for the second one. The first one, the force 1, is going to be causing a clockwise, which will be negative. The force 2 will be causing a counterclockwise, which will be positive. Same kind of thing. So both of these are going to have a sine of an angle attached to them as well. And all of a sudden, when is this homework assignment due? It's Wednesday. Okay, good. So that's kind of how to go about that. Let's take a look at the rest of chapter 9. I don't think we quite finished it, did we? Not really. So let's go in there and take a look at it. So we're going to finish up chapter 9 today and start chapter 10. I think we can actually have chapter 9 homework due a little bit earlier than is stated here. It's only 6 or 8 problems. Let's take a look here in the calendar. If we get chapter 9 due a little bit earlier, we can hopefully get it done by tomorrow. Then we can start chapter 10 and have questions for chapter 10 on Wednesday. And that would be really good. Because then we could have you taking chapter 10 exam and be I don't know how much homework, how much there is in chapter 10. Let's see how much there is in chapter 10. Okay. So yeah, I think that'll do. We'll make chapter 9 due on Tuesday, and we can answer any final questions that you have on those tomorrow before lab or during lab or whatever if we have to do that. But chapter 10, we can get started a little bit early and have questions for chapter 10 on Wednesday in class. Exam coming up due by next Friday. Just so you know, I will be traveling next Friday and Saturday, so I may not be answering emails as regularly as I normally do next weekend. We need to get a few more homework assignments into this. Why is this one missing so many? I think I actually know what's wrong with this. I think I need to look at my fall physics 1410. This one actually will work. Yes, there are all the other ones. Oh, I wasn't able to fix it there either. I will try to fix the wheelbarrow one today. See if I can get it done. But we have 12, 13, 14, 15, 16, 17. We do have some chapters, some homework chapters that we'll put into this one. In fact, I will do it right now. Might as well. Export. Nope. Copy from Okay, sorry, I'm kind of getting off track here a little bit. I want to do this though really quick. So math 14 to 10. Select items. Copy. All right. So, we've got our rest of our chapters in here. Okay, where are we at here? Let's go back to sharing our desktop. All right, so anyway, let's go back to the book and get finished with chapter 9 here. So essentially what we're going to do is do some examples. So we'll see a lot more of these torque problems really quick, or a few more anyway. And here they show us the problem solving strategy. Determine whether or not the system is in static equilibrium. Essentially, if it's rotating or acceleration in any direction, it is not static equilibrium. If it's not moving at all, of course, it is in static equilibrium. But if it's moving in a constant velocity in a straight line and has constant constant rotation, it's not changing, then that's equilibrium. It's just not static equilibrium. Okay, so anyway, we want to draw our free body diagram, make sure that we label forces, and make sure that we know all the stuff that we know, but also where the forces are applied. We need to know what the distances are to the forces, the angles of the forces, and everything for this when we're talking about forces and torques combined. And then we have two sets of equations. The net force equals 0, that can be force in x equals 0, and forces in y equals 0. And then all the net torques. Add all the torques together, and that has to equal 0. So now we have three sets of equations we can build, and then we can solve them for the things that we want to know. And then check your solution here. So here's a problem where we have different situations. We have this person holding up this bar, and at first they hold the bar in a nice even way. This is how you would want to hold a bar because it gives you a balanced force in each of your hands. The center of mass right between your hands, the center of mass of the bar, if it's right between your hands, equal distant to both hands, then your left hand and your right hand will be holding up an equal amount of the weight of the bar, right? Each one. However, if you set it off a little bit, offset it a little bit, then if that center of mass is closer to your right hand actually has to bear more of that weight. In other words, there's an uneven distribution of forces here. The left hand has to bear less of the weight. If you go really off kilter, then you have to switch your hand grip. And you've probably done this before. If you're a pole vaulter, you've definitely done this before, where you have to switch your hand over because your fingers aren't quite strong enough to hold up the weight. So you flip one hand over, and this hand is actually pushing down on the bar while this one is pushing up on the bar to hold this weight. And notice that these forces all of a sudden become much bigger than the actual weight of the bar, whereas up here, the forces of your hands and the weight of the bar added together to equal 0. So in this case, we had all these forces adding together to 0, all these forces adding to be 0, but this one, huge forces, and a much smaller force. It turns out that these still add to be 0. But this one is a positive, this one's a negative, and they add to be 0 with this. So these two add together to equal this one. It just doesn't seem like it at first. But in all of these cases, the torques also add to 0. So in this case, we have two torques we have two torques from your hands. If we're saying the center of the bar is our rotational point, then this one is going to cause a counterclockwise rotation. This one is going to cause a clockwise rotation. So this one's positive and this one's negative, and this one's going to cause no rotation because it's acting at the center of the bar. So those two torques will cancel out. If we look at this one, and we say the center of the bar is still our point of rotation, then this one's going to cause a huge torque to the left, to the clockwise, counterclockwise, which is positive. This one's a small torque to the right, well, a small force that will cause a torque to the right. But these two torques are still going to be equal because this distance is small and this distance is big. So still same equal torques. If we look at this bar, then we have, and we're measuring from the center of the bar, then we have this one upward is going to cause a counterclockwise rotation, big force, fairly big distance, smaller force but bigger distance is going to cause a clockwise rotation, which is negative. So negative plus positive torques, again, those torques are going to equal each other for a total of 0 torque. And here they actually show the math for this. We're going to look at A, right hand, B, left hand. So we're doing figure 919, which is this one right here, where he's got one hand pretty close to the center and another one a little bit further away from the center. Not much further, but a little bit further. And here they tell us the hands are 0.9 meters apart, so the distance between the hands is 0.9 meters, and the center of gravity is 0.6 meters from the left hand. So 0.6 meters from here, that means this hand is 0.3 meters. So we know the distances. We know distances, we know that the angles are all 90 degrees, we can calculate the torques. We know that one torque is going to be equal to, is going to be a positive torque, we know the other torque is going to be a negative torque, and so we get a torque, we get the torque from the right hand added to the torque from the left hand equals 0 if we're measuring from the center. Let's see what they actually do. Net torque equals 0. They're saying if the pivot point is chosen to be at either hand, they chose to locate the pivot at the left hand. So in their problem, instead of saying that we're going to measure from the center of gravity of the bar, they're going to measure from the left hand. That's perfectly fine. You can measure from wherever you want. So if you measure from the left hand, then the left hand is not going to exert any torque. And it's just these two forces, the force from the right hand and the force from the weight. Force from the right hand is going to be a positive torque. Force from the weight is going to be a negative torque. Remember that positive torques cause counterclockwise rotations, and negative torques cause clockwise rotations. So when they're done, they get they actually create an equation that says the clockwise rotations have to equal negative the counterclockwise rotations, which is the same as saying add all the torques together and equal 0. In any case, we get the torque from the right hand equaling negative the torque from the weight of the bar in the end. The torque from the right hand, since the right hand is 0.9 meters from the left hand, and that's we're measuring everything from the left hand, then you put 0.9 meters times the force of the right hand equals 0.6 meters times mass times gravity of the bar, because that's how far the bar is from the left hand. And that's our equation essentially. Why is one of these not negative since this has a negative sign on it? Well, because the weight of the bar, in this one is down, so that's a negative force. And the force from the right hand is up, so this one, the weight of the bar, which is on the right hand side, was a negative, and that negative combined with this negative to make a positive, so now we have a positive. In the end, we're solving for the force that the right hand exerts to hold this thing up, and then we divide both sides by 0.9 in the end. So we get 0.667, which is 6.6 times 0.6 divided by 0.9 is 0.667. And then we multiply by the 5 kilograms bar times the 9.8 meters per second squared of G. We get 32.7 newtons. Once we figure out the force on the right hand, then we can use the sum of the forces equals 0 to calculate the sum on the force on the left hand. The sum of the forces said we have two upward forces, which are positive forces, force left hand, force right hand. Then subtract the weight of the bar equals 0. And then we just solve for this, for the force on the left hand. Ends up being 16.3 newtons. And that's how all of these problems go. Usually you start off with a torque equation, not always, but usually. Sometimes you can start with the force equations and get something really quick out of them. You just kind of have to look at the problem and see what you have and what you're looking for. But in the end, you're using sum of the forces in x equals 0, sum of the forces in y equals 0, and then the sum of the torques from any given point, from any point that you would choose, equals 0. Now machines, simple machines, which you've probably studied at some point in some science class somewhere, are designed to take advantage of torque. And this advantage we call mechanical advantage. So here's a very simple example, is the lever bar, right? You have a nail puller, or whatever you want to call it, a crowbar. And we're going to slip this thing under a nail on this short end, and then the long end we're going to press on it. Why do we say short end and long end? Because at the point of rotation, which is right here, right next to the nail is the point of rotation, you have the normal force of the board pressing up on the bar. On the short end, you have a huge force that is applied from the short distance to the normal force on the wood. And then we have a long distance and a small force. You just push with a small force on the long end of the bar, and on the short end of the bar, there's a huge force applied. This is a torque, right? We have a torque from a distance, from a force, there's an angle. We have a distance, there's a force, there's an angle. And in the end, if we want to calculate this, it ends up looking like distance times force and distance times force, where we say the distances are going to be the horizontal distances out to the force. And we can solve these in several different ways. We can solve it for force over force, or distance over distance. It ends up being the force. So we have an O and an I here. The O stands for in and out, I believe. So the force in and the force out, input and output forces. So this is the force in. This is the force that I apply to it with my hand. And the force out is the force that comes out on the other end of the machine. The distance in, or the length in, what they're calling it, Li, is the distance from the rotation point to my hand, where I'm applying the force, L in. And then the distance out is the distance from that rotation point to the output force. So what they get when they solve this for forces on one side of the equation and lengths on the other side of the equation is that they get the force out over force in equals length in over length out. There's this inverse effect going on here. And mechanical advantage is equal to either one of these. So mechanical advantage is the amount of advantage that you get from using a machine. So you take the amount of force that you get out, divide it by the amount of force that you put in, and you get the amount of mechanical advantage for a crowbar. Or you take the length of the handle, the length of the crowbar from the rotation point to the nail, and rotation point to the handle, to where the hand is pushing, divide it by the length of the rotation point to the nail, and you will also get the mechanical advantage. So in machines where you get a bigger force out than you put in, you get a mechanical advantage that is greater than 1. So this might be a mechanical advantage of like 10 or 20. The bigger the advantage, the more force you get out on the other end. And this is true of scissors, this is true of hammers, it's true of pliers, wrenches, all kinds of things. Sometimes there are machines that actually have a mechanical advantage of less than 1. And the idea there is not necessarily to get a lot of force out, but to get to be able to move something Let's see, what's a good example of this? One example of this is to get something to move a long distance with a lot of force. That's so. So here's an example. Let me show you an example of this. On a front end loader. If you look at a front end loader, which is a piece of large equipment here, you have this big bucket on the front that needs to move a long distance. But the force that is applied to this thing is applied way back here. Instead, I mean, you can't just lift it from here. You can't lift it on the long end of the lever handle. You have to lift it back here where your hydraulics are. So to lift this thing up, it's like lifting at the, it's like lifting on the, it's like trying to lift this bar up by pushing on this tiny end here, which is very hard to do actually, even with a small crowbar. So what they do is they put a huge force here using hydraulics, and then they lift the bar up a long way, and that's how the bucket lifts a long way. Okay? It lifts a long way using this huge force at the other end of this tiny little lever arm here. But that's a good thing because then you don't have to have your hydraulics sticking out in front of the front end loader. It would be really bad if you had to do that. It wouldn't be well designed. It's the same thing with our arm. Our arm here has this, remember we did this thing here, and you can do this with me again. If you're holding up your arm horizontal to the ground and you press your finger in here, you feel a really, really tight tendon. And the reason for that is because the distance between the rotation of your arm and where that tendon is only about an inch and a half. Not very big, very short distance. If our tendon could go all the way out to our wrist, then we wouldn't have to pull so hard. The tendon wouldn't have to be so tight because it's easy to lift your hand out here. It's easy to lift your arm out here. It's hard to make it lift from here. If you try to relax and try to lift your arm with your finger from here, don't use any of the muscles in one hand, just try to lift it with your finger, it's really difficult to do. It's really difficult to do. But your tendon can do it by applying a huge amount of force right here. So why don't we do this? Well, if we didn't have this connected here, if we had it connected out here so it could be nice and loose and still lift up our arm really easily, then we'd have to have this funny skin thing going on between our, we'd have a big web of skin between our wrist and our shoulder. It wouldn't work out so well, right? There are animals that have that. Can you think of an animal that has a tendon that connects way out here, and so they have this thing of skin between their like joint and their bone? Can you think of any animals that have that? Bats do. Even closer to home. How about a horse? If you look at a horse right here, there's this flap of skin right in there, right? We don't have that. And in fact, it's one of the big differences between four-legged animals and two-legged animals. Animals that walk on two legs have very, very different structure. And the horses have this big flap of skin right there. They have another one back here. And that's what actually, it's actually easier on their bones and muscles to run. Much harder on us. But we have distinct advantages. Here's another one. It's even more so. The kangaroo definitely has, if they stretch out their leg right there, you'll definitely see it because it goes from like right about here to almost their knee when they stretch out, when they're jumping. You can see it kind of right here. There's this skin right here. Their bone goes this way. This flap of skin goes this way. Birds have it. All kinds of animals have it. Just about every animal has it, except for like humans. And why is that? Well, because their bodies are designed to jump very quickly, and ours are not. Their bodies are designed to make that leg move very quickly. They have to survive out in the wild We're not designed that way. We were not designed to survive in the wild by our physical instincts, by our physical attributes. We were designed to survive by our brains. Our brains are what make us to survive, right? So, very different design. Oh yeah, machines. So other machines. Here is another machine. Here's the wheelbarrow. You have your wheel here. You have the length out to where you lift is a very long length, and the length to the thing that you're lifting is a short length. And that's ideal. You really don't want that to be very long, and you want this to be as long as it possibly can be to make it easier to lift. Shovels the same way. You're going to rotate this around this hand here by pushing on this hand here and leaving this one just holding it, and that's your weight. Simple machines. In fact, just about everything is a simple machine in some way or another. So here we have the wheelbarrow problem, and they're doing the mechanical advantage of the wheelbarrow equation and they're going to solve for the force in that equation, knowing everything else. Here's another one. This is what we call a wrench. It's a crank lever. Here you have this rotating thing here. We have a force that you're pushing up on with here, and then there's a force down on the other end of the handle that turns a bolt, or it turns a shaft or something like this. And this is the distance between them right here. So there's a distance here, and there's actually a radius here. There's a small distance here. Here you have the wheel on your car. You have the radius of the wheel of the car, which is one of the distances, and then the radius of the wheel on the actual axle is the other distance. So the ratio of those distances. Pulleys. Pulleys are interesting because you can have different size pulleys, and that can give you different size torques, essentially. But pulleys are also interesting because when you connect a pulley, if you connect a single pulley to the roof like this, then you have the force that you pull down with is going to transfer itself around the pulley and be the force that pulls up. So having one pulley doesn't really give you much mechanical advantage, except that you can use your weight to pull down, right? You can actually just sit on it and use your own weight. That's the only advantage it really gives you, if you have one pulley. However, if you have two pulleys connected like this, where you tie the second pulley to the first pulley, then go around the second pulley and then go down over atop the first pulley and then down, now you have two ropes pulling up on whatever it is you connect to the second pulley. So if you pull here with 10 pounds of force, you'll be able to lift 20 pounds. If you put in 3 pulleys and you pull with 10 pounds, you'll be able to lift 30 pounds. 4 pulleys, you'll be able to lift 40 pounds, and so on. Right? So multiple pulleys allow you to pull very, very big loads. The distinct disadvantage to this is that you have to pull a longer distance. For this one, you have to pull twice as far to get this to go up half as much, because each of these ropes has to move 5 inches for this to move 5 inches, right? So this rope ends up moving 10 inches. So there's the difference in advantage. You pull this 10 inches and this will move up 5 inches, but you only have to pull with half as much force, right? On these ones, this one here, you're getting 4 times as much, but you have to pull it 4 times as far to get this thing to move. You know, if you want this to move 1 inch, you have to move this 4 inches. And you see this, you'll see these all the time on boats, for example, when you're lifting sails up on a sailboat. Sails can be very heavy, and once you start lifting them up and the wind catches them, it can be really hard to pull them up. So sails often have, these are called pulley blocks, and you often see those, and you'll see people pulling, and they're pulling like crazy, and their sail's only going up a little bit at a time because they have to pull through all that extra rope. Now, here is the last section, I believe. Yep. And this is going to be our lab for tomorrow. So here is the example we've been talking about a couple of times, where you're holding something up in your hand, and you have this bone, this muscle from your bicep is the thing that holds up the entire arm and whatever you have laying on it, essentially. One muscle does that all. And it's connected just a couple inches, 4 centimeters, about 1.5 inches. It's connected just a couple inches from the elbow joint, which is the rotation point. And this force on the bicep muscle pulls up this way at about 90-degree angle. Then you have the weight of the arm, which pulls downward at a 90-degree angle, about halfway out. And then you have the weight of whatever's in your hand that pulls downward on your arm. So this one right here is trying, so remember, this is our point of rotation. So this one's trying to create clockwise motion, counterclockwise motion. So that one's positive. Then these two are clockwise motion, so they're negative, right? If you redraw this in a simpler diagram, you have your point of you have your point of rotation right here, which is your elbow. And there is a force on the elbow, but it's not going to create a torque because it's right at our point of rotation. And then there's a force upward from the bicep, the positive torque, the weight of the arm down, negative torque, weight of the book down, negative torque. And so the torque equation ends up looking like this. We have the R2 and the weight of the arm, that's this one here, weight of the arm, R2, weight of the book, RB, or R3, that's distance 3, and then you subtract off R1, force of the bicep, or you subtract off these two, and then you set it equal to 0 and solve it, which is what they've done. Let me actually do this for you really quick, because they every time in this book they skip a step and they just jump straight to this, but I want to actually show you the step. So here's the arm, here's the elbow. There is a force on the elbow. The bicep is going to push upward, is going to pull upward. This is the force of the bicep. And there is a force from the elbow pushing down on the bone here. And then there's and we'll call this R to the bicep. And then we have the weight of the arm down this way. And we have the weight of the book over here. And we have a distance to the arm, center of mass, arm. And we'll have distance to the book, which we'll call R. We'll use capital B for distance to the book, and we'll use capital B for the weight of the book. Right? So here's all our forces, here are all our distances. And the sum of if we do the sum of the forces in the y direction, because those are only directions we have for our forces, then we get force of the bicep, which is a positive force, minus force of the elbow, which is a negative force, minus force of the arm, which is a downward force, and minus force of the book. So, and that has to equal 0 because the arm's not going anywhere, not mass. No acceleration, so mass times acceleration equals 0. Here's all of our forces, and you see that the force on the bicep, here's the book, not the bicep. The force on the bicep has to equal all these other forces for this to equal 0. All these other ones have to take away the force on the bicep. In other words, the force on the bicep is going to be pretty big. Then the sum of the torques equals 0 is going to be the torque from the torque from the elbow, since that's a distance of 0 to our, we're going to measure all our distances from here. The torque on the elbow just becomes 0 because it's at our 0 point. The torque from the elbow. Then we have plus the torque from the bicep, and it's a positive torque because it causes this rotation around this point that is counterclockwise. And then we're going to subtract off the torque from the weight of the arm, torque from the arm, because this one's a clockwise one. So the clockwise are negative, and then minus the torque from the book, which is also a clockwise torque. It's causing this clockwise rotation. So those are both negative. This is going to result in this equation right here. Torque from the bicep equals torque from the arm plus torque from the book. And that's what they have in the problem. That's what they write down. They just write it as all the clockwise torques you have to equal all the counterclockwise torques, which is true in static equilibrium. It's not true in the next chapter, so that's why I don't like to teach it that way. But that's the equation they're starting with. And that's that equation right here. So that this is the torque on the arm. This is the torque from the arm. This is torque from the book, and this is the torque from the bicep. And we're going to solve for the force on the bicep because we know the distances to all three of these, and we know the weight of the book and the weight of the arm. So they throw it all in there after we've solved it, and we get a force on the bicep at 470 newtons, which is, significant. It's like 100 pounds. The bicep has to have 8 times as much as the weight. So if you have the weight of your arm and the weight of the book, you have to multiply that times 8. It's almost 10 times, the bicep has to lift almost 10 times more than your arm is actually lifting in order to lift that. Is that 10 times different? And that's not a mechanical advantage. The bicep has to work harder to lift something in this case. But what is the advantage? The advantage is that we have a lot of movement in our arm. We have a lot of movement here. And we don't have to have our tendon way out here. Right? And that is actually a huge advantage. While horses and kangaroos and other animals like birds, while they can actually, while they can move very quickly, very fast, in a very short amount of time for a very short distance, they don't have nearly the ability to move long distances that we do. So this is one of the reasons that humans have survived as long as we have. We can move very long distances, and we can do very, very complex motions with our bodies. There is no animal that has ever climbed any of the biggest mountains in the world. You take the top 10 biggest mountains in the world, there's not a single mountain, single animal that has ever been to the top of them, except for humans. Because we're the only ones capable of doing it. And this has a huge part of that. So the mechanical advantage, while it is not an advantage for strength or even speed, it is an advantage in many other ways. Particularly ability to move, the agility of motion. We call it mobility, right? The mobility of the human being is far greater than the mobility of any other creature. We're much more versatile. So the back is another one that's hugely important. So this is a nice picture of the back. You have all these bones in here, and in between each of these bones and around these bones, surrounding these bones and connecting them all to everything else, are a bunch of tendons and muscles. These muscles are at extreme angles to the back. Right? You don't see any of the tendons in your back or anything like that, but we're often lifting our body weight as we bend over to lift something up, as we twist around to grab something, and as we do that, even if we're not lifting something up, even if we just bend over and lift our own body weight up, our back has to do all of that with these muscles that are really extreme angles, and that extreme angle causes a huge amount of force in the muscle and a huge amount of tension in the tendon. The back has more tendons that are under extreme tension than any other part of the body. Right? This is the reason for backaches. This is the number one reason for backaches. It's not the spinal column. The spinal column doesn't feel pain usually, hardly at all. It doesn't really have the right kind of nerves for pain. It's not the bones. The bones don't usually feel pain either. Unless you've really done something to damage your back bones, and create like a compaction of the cartilage in between them. Unless you've done something really bad to your back and there's bone rubbing on bone, it's not the bones that cause pain in the back. It's the muscles and the ligaments and the tendons. The ligaments hold the bones together. The tendons hold the muscles to the bones, right? As those things get stretched and strained, or torn, or ripped even, that's what causes the pain. As the muscles get cramped, and as the muscles get torn, and as the muscles get stretched, that's what causes the pain. So the number one cure for back pain is not chiropractic. What they do and what a chiropractor does for you is he just rearranges things and massages it, makes it feel better, and then that's it. The number one thing is to exercise the back, so you have strong muscles and strong tendons. Another thing that's bad for the back, again, is stretching the back, because when you stretch the back, then the tendons tend to be longer than they need to be, and then your muscles have to work harder. So doing a lot of stretching of the back is not a good idea. You know, people think, oh, these gymnasts, you know, they're so flexible. They must be so healthy and so strong they can do all these flexible things. Every gymnast, by the time they're 30, their bodies are destroyed. Their life is over at the age of 30. Men's and women's. Gymnasts are in the worst health of their lives after their career is over. And even during their career, you can tell because they're all strapped up and bandaged up all the time. The only ones who aren't are the ones who are in the Olympics. And it's usually because they're just so young that they're having damaged themselves. You know, the average age of a female gymnast is like 15 in the Olympics. And they keep lowering the age so that they can do more amazing things. And for men, it's like 18 or 17 or 16. It's just insane. They're doing crazy, dumb things to their body by forcing their body to be so flexible. It's not a good thing. You really want to have things, you want to have your bones tightly bound together by tight ligaments. They don't want to be so tight that you can't move, but they want to be good and firmly tight so that your bones don't slip. So that because once your bones slip in your back, then things get in between them, like nerves, and then you smash those nerves, and then it really hurts. But if you don't allow things to get in between, you keep things strong, keep things tight, you can have a nice, healthy life for a long time. And you know, people who don't have bad backs, generally, and people think, oh, they always have bad backs, but people who don't have bad backs are usually people who get a lot of exercise with their backs, who do a lot of lifting and they lift things properly. If you bend over and lift something up, you're going to put a huge amount of strain in these muscles. You can see that angle right there. It's like pushing the door closed from the side all the time. You have to apply a huge amount of force, and that starts to rip things. But if you lift things properly and you don't try to overlift and you do a lot of it every day, you're going to be pretty healthy. So people that work in construction, people that work moving around a lot and lifting a lot, you know, doing things like that, they tend to be in much better health. So that takes us to the end of the chapter, and we are done. Now tomorrow we're going to do a lab where we actually set up a fake arm. We didn't do this already, did we? No. So we're going to set up a fake arm, and we're going to do make a bunch of forces on it, and we're going to do some measuring and calculating and do some experiments with it. It's a very demonstrative lab, and I really like it a lot. Does anybody have any questions for, let's see, we need to start chapter 10. Are we going to do chapter 10? What the heck is our calendar say? So our calendar says chapter 10 on Friday, so we need to start chapter 10 a little bit today. Yeah, so we're done. Does anybody have any questions for chapter 9 before we start on chapter 10? Okay, let's start chapter 10 a little bit. Let's see what... This chapter 10 is very related to chapter 9. What we're going to do now is we're going to take the stuff that we've learned about rotational motion and essentially do some kinematics and dynamics with it. So we've already talked about measuring angle in radians. We've talked about angular velocity, omega, which is the change in angle over time, right? We've talked about the relationship between angular velocity, something that's rotating, and how fast something is moving along the edge of it. So this is what we call tangential velocity. So tangential velocity equals the radius of the thing that's rotating times the angular velocity of the thing that's rotating. And then, of course, you can mix that up and solve it for the angular velocity. V over r equals angular velocity. But we haven't really talked about angular acceleration. What if something is rotating and the rotational speed begins to increase? It rotates faster and faster and faster. Well, that is going to be called alpha. We're going to call it angular acceleration. And it's going to equal the change in angular velocity over the change in angular time. Or over the change in time, not angular time. Sorry. And let's just do a quick example of how we might use that. We have a teenager that slips their bicycle upside down and they're spinning the wheel like kids do sometimes. And they start the wheel spinning from rest, so it's not spinning to start, and then they start it up spinning to a final angular velocity of 250 RPM in 5 seconds. What is the angular acceleration in radians per second squared? So 250 RPM, remember that's rotations per minute, so that's not in any kind of units we want to use. We want to switch that into radians per second. Rotations, there's 2 pi radians per rotation, so that's our first conversion, 2 pi radians per revolution. And then there's 1 minute per every 60 seconds. So we multiply the 250 times 2 pi, we divide it by 60, we get 226.2 radians per second is how much we've changed our omega. We went from 0 to 250 revolutions per minute, or 0 to 26.2 radians per second. So that's our final angular velocity right there, or our change in angular velocity, 26.2 radians per second. And alpha is equal to that number divided by the time that it took. It took 5 seconds, so we divide by 5. Get 5.24 radians per second squared of angular acceleration. Now, in the second part, we're going to stop the wheel. It says that we stop the wheel from, we're going to go from the final 26.2 radians per second down to 0, and we're going to do that with an angular acceleration of negative 87.3 radians per second squared. So that's going to tell us how much angular acceleration we're going to have as we stop. And we're going to rearrange this equation to do this for a stopping time. Here's the rearranged equation. For a stopping time, we're going to go from 26.2 down to 0, which gives us a change in angular velocity of negative 26.2 radians per second. We're going to do it with 87.3 radians per second squared of angular acceleration with a negative on front. Divide those two and we stop it in 0.3 seconds. So we've just rearranged the equation for angular acceleration to solve for delta t. And this should look familiar. This should look very much like linear acceleration and linear deceleration, right? Linear speeding up, linear slowing down. This is rotational kinematics. It's not really any different than it was before. Now, if we have angular acceleration, then of course we're going to have tangential acceleration, or the linear acceleration as well. And look, it turns out, if we do the math, it turns out to be the same thing. Tangential acceleration equals r times the rate, angular acceleration. And if we want to solve it the other way, angular acceleration equals tangential acceleration divided by r. It's still the same way as it always was. So if we have a motorcycle that is accelerating, and their linear acceleration goes from 0 to 30 meters per second, what is their angular acceleration going to do? Remember that the linear acceleration is the tangential one, and the angular is the alpha, right? So we have a linear one of 0 to 30 meters per second, so that's 30 meters per second in 4.2 seconds. Calculate that tangential acceleration as a delta v over t, and it gets 7.14 meters per second squared. Then we set that equal to alpha by dividing by r, because tangential acceleration divided by r is equal to alpha. And that gives us our angular acceleration of 22.3 radians per second. So this equation can be used in two different ways. You can change linear to, or angular to linear using this one, or linear to angular, which is what we just did using this one. Just rearrange. In this case, we knew the linear because they told us the linear acceleration. They give us information to calculate the linear acceleration. And then we used the conversion back to angular acceleration. And they actually... So here is a table of those. We have our translational variable, which is x or y or whatever. But in linear or in rotational, it's alpha. It's goodness, I can't speak. It's theta. So we have translational x, rotational theta. The relationship is theta equals x over r, or x equals theta times r. We have rotational is omega, translational is v for velocity. The relationship is v is omega is v over r, or v equals omega times r. And translational we have, rotational acceleration we have alpha. Translational acceleration we have a, and the relationship again. It's always divide by r to get the angular, multiply by r to get the translation or the tangential. Either way you want to say it. So how do the kinematics feel? Well, it's pretty simple. It's actually the same. Here is the rotational, or here's the translational. X equals velocity times time, average velocity. In rotational, it's theta equals angular velocity times time. In translational, you have v equals velocity final equals initial velocity plus acceleration times time. In rotational, we have angular velocity equals your initial angular velocity plus angular acceleration times time. Everything just turns to angular. It's the same equation. Instead of v, you have omega. Instead of a, you have alpha, and everything else is the same. This one, you have your final position equals your initial velocity times time plus 1/2 at squared. This one, you have your final angle equals your initial angular velocity times time plus 1/2 alpha t squared. And this assumes that you start off at an original position of 0 and an original angle of 0. Right? And then you have this one. You have your velocity final squared equals your initial velocity squared plus 2 acceleration times your displacement. And in this one, you have your final angular velocity squared equals your final initial angular velocity squared plus 2 times the angular acceleration times your angle and theta that you move through. You also have definitions for your average velocities here. Average linear velocity, average angular velocity. And you're going to go about solving kinematics the same way in rotational as you would in linear, except for one thing. You often have linear and angular mixed together when you're doing angular stuff. They're often mixed. So here's an example. The fishing reel, right? With a fishing reel, you have, of course, the fishing reel, oops. The fishing reel itself rotates around and around, right? As you're reeling something in or letting something out, letting line out. The fishing reel itself rotates around its center axis. However, the fishing line that's either coming in or off of the line, off of the reel, is moving in a straight line, right? How do you relate the velocity of this straight line movement with the angular velocity of this around movement? Well, you use the relationships we were just talking about. V equals r times omega, or omega equals v over r, right? What if this is speeding up? What if this has some angular acceleration, alpha, which means this would have some linear acceleration, a? Well, then it would be the same thing. It would be linear acceleration a equals r times angular acceleration alpha. And if you rearrange it, angular acceleration alpha equals linear acceleration divided by r. Right? What if you want to know how much of this, let's say that we know that 20 meters of this or some length, let's say that we have some length of this in X, gets wound up. How many times will this go around? Well, if this is X, then the amount of angle that this thing goes around is theta. And the relationship, again, is X equals, whoops, I did this wrong, didn't I? Sorry, I did this second one wrong. This should be R, goodness, R times, what did I, oh, no, that's right, I did that right, sorry. That is right, okay, sorry. So in the last one we have X equals R times omega, or R times theta, and then if we wanted to solve for theta, theta equals X divided by R. So if you knew how much line you dragged in here and you knew the radius of this, and you know the radius of this reel, you could actually figure out how much angle it goes around by taking the distance of the amount of line you pulled in and divide it by the radius of this, and that would tell you how much theta this thing spun. And for every 2 pi theta, it spins around once, right? For every 2 pi radius, it spins around once. For every theta equals 6.1, 6.28. It went around once. But anyway, that is what we're doing here. You have some new kinematic equations and some relationships between the two. So let's go back and do an example. Here's the first example, the acceleration of a fishing reel. So we have a deep sea fisherman hooks a fish that swims away from the boat, pulling the fishing line from his reel. The whole system is initially at rest. There's no acceleration, there's no movement at all. The fishing line unwinds from the reel at a radius of 4.5 centimeters from the axis of rotation, and the reel is given an angular acceleration of 110 radians per second squared for 2 seconds. So what they've told us is how fast it's spinning, the acceleration of the spinning, and they've told us the time. What does that mean they've told us? That means they've told us, well, so far they've told us R, the radius. They've told us alpha, right here, and they've told us t. Well, from the radius and alpha, we can figure out acceleration A, because it's related, right? A equals R times alpha. So we can calculate A, but what they want to find out first is what is the final angular velocity of the reel. We're going to need a kinematic equation for that. If we know the acceleration, the angular acceleration alpha, and we know the original one right here, this is the original angular velocity, which was 0 because it started off not moving, and we know the time, then we can calculate the final angular velocity. So this is part A right here. This equals 0. This is our time. This is our angular acceleration. That's what we're solving for. Part A. So we come down here to part A, and that's exactly what they use. They plug in their numbers, 0 for the initial, 110 for the angular acceleration, 2 seconds, and they get 220 radians per second of angular speed when it's done accelerating after those 2 seconds. In part B, they want to know what speed is fishing line leaving the reel after 2 seconds. So after 2 seconds, we have this angular velocity, omega, 220 radians per second. What is the linear velocity that's associated with that? Well, linear velocity equals angular velocity times r, the radius of the reel. So we multiply by the radius of the reel, 9.9 meters per second. That's how fast the wire is coming off the reel. How fast the line is coming off the reel, 9 meters per second, almost 10 meters per second. That's really cooking. Holy moly. Have any of you been deep sea fishing? In deep sea fishing, they actually keep a jug of water next to the reel. The reel is usually about this big. And that reel, it can crank out like thousands of yards of line. But this thing gets going so fast, and when they start applying the brake to it, it will actually start to smoke. So they actually pour water on it. It's actually it's a water-cooled reel. So they are constantly pouring water on it to keep it cool. Because big fish, if you get a tuna or a shark or something on your line, man, it can really pull for a long time and really fast. So it's pretty impressive. And if it's a shark or a tuna, you definitely want to reel it in. Because them's good eating. Have any of you ever had like fresh tuna or fresh shark, like a tuna that you cook instead of coming out of a can? Like I don't know why anybody eats tuna out of a can because it doesn't taste good at all to me. But tuna fresh, like grilled on a barbecue or broiled in an oven with some sesame seed and oh man, it's so good. Some soy sauce is perfect. Soy sauce. And shark is fantastic on a grill with a little bit of lemon and pepper. Ooh, wow, so good. Anyway, okay, so making me hungry. Now I'm going to eat some fish. So that's part B. Part C, we want to know the number of revolutions. Well, they've told us, we know the speed that the thing is spinning. We know the speed that the line's coming off. We don't know how much line is coming off. So we need to go back to our equations. We need to know how much line has come off. That means we need to know, we need to know how many times it's spun around. That's what they want to know. They want to know how many times it's spun around. That's how much angle. So these are our equations for angle. This one has angle and this one has angle. But we don't know the average speed really because we do know that we can calculate the average speed, I guess. So I suppose we could use that one. But I think we want to use this one, which uses the initial speed, the time, and the angular acceleration to get the final, because we don't want to mess with anything else. So we go ahead and do that, and that's the equation they use here, right here, and they plug in all the numbers. We know all those numbers again. The number of meters of the fishing line. Well, that one we take the amount of angle that came out, that it rotated, and we multiply it by r again. So we know it goes through it goes through 220 radians of angle, and we multiply that by the 4.045 meters to 4.5 centimeters. We get 9.9 meters of fishing line comes off during that acceleration. So it's very similar to kinematics before, where you're looking for the right equation to get the right number out. You might even have to use two equations to do something. But oftentimes you're gonna convert over to translational using the translational equivalent by multiplying the angular stuff by r, or you might divide the translational stuff by r to get the angular. Either way. Here's another one. Fisherman applies the brake, achieving an angular acceleration of negative 300 radians per second squared. How long does it take the reel to come to a stop? That's another kinematic equation. It's this one right here. You're starting off at omega 0 is 220 radians per second, and you're going to slow down to 0. That'll be your final, and then you're going to solve for t, which is what they do. Here's one where you calculate a train accelerating from rest. It has 0.350 meter radius wheels, an angular acceleration of 0.250 radians per second squared. And after the wheels have made 200 revolutions, we want to know how far it's moved and what is the final angular velocity. Well, how far it's moved is we have a theta is what we're going to want to calculate, because theta is going to be just a conversion, right? We have 200 revolutions times 2 pi radians per revolution, so it's 1257 radians that it rotates through, so it goes through 200 revolutions. And then that's the angle, and we just calculate x by multiplying by r, the radius of the wheel, and get 440 meters. So 440 meters down the track, that's a quarter of a mile, right? And then they want to know how far, they want to know in part B, what's the final angular velocity and the linear velocity of the train. What's the angular velocity and the linear velocity? Well, they use another kinematic equation, which gives us our final angular velocity if we know our initial angular velocity, which is 0, and if we know the angular acceleration and the theta. So we know all those things, we can calculate the final angular velocity. We do that, get 25.1 radians per second for that final angular velocity after a quarter of a mile. And what's that translate to in a linear velocity? Well, we multiply the angular velocity by r again to get linear velocity, and we get 8.77 meters per second, which is not very fast, less than 20 miles an hour. So we need to speed up a little bit more. It's not going anywhere. After a quarter of a mile, a car in a quarter of a mile can go from 0 to 60 pretty easy, 60 miles an hour. But a train, 20 miles an hour that's pretty good speed actually. Like the trains coming out of North Platte are definitely not going that fast because they're so loaded down with coal. Probably going 10 miles an hour after a quarter of a mile. Take them a lot longer to get up to speed. So anyway, that's kind of the idea with the kinematics rotational motion. Now, what happens when we start talking about dynamics of rotational motion? So kinematics is just about the movement. Dynamics is what causes the movement. Well, what causes rotational movement? What causes rotation? A force acting at a distance from a rotational point, a torque, right? Torques cause rotational motion. So here's an example. We have a person pulling on this wheel up here, but it's rotating down here. So there's a distance between the center of the wheel and where the force is applied. The force is applied this way. There's a 90-degree angle between the force and the radius. And that way, we're going to get a maximum amount of torque there. Force equals mass times acceleration. But if we replace normal acceleration with rotational acceleration, remember that normal acceleration equals r times rotational acceleration, we get this thing, force equals m times r times alpha. Right? So we have force equals m times r times alpha. That's not exactly Newton's second law. Newton's second law equals force equals mass times acceleration. We've got an r sticking around in our equation. And this acceleration is not a linear acceleration, it's an angular acceleration. But what if we multiply by r on both sides? If we multiply by r on both sides, we get r times f equals m times r squared times alpha. Well, that looks a little more interesting because now we have, on the left side, we have the kind of force, quote unquote, that causes rotation equals something times the angular acceleration. So we have kind of like a rotational force with something times rotational acceleration. So this almost looks like Newton's second law. Torque equals something times angular acceleration. This something has mass in it, but it also has some distance in it. It has this distancing thing in it. It turns out that we're going to call that distancing thing, that mr squared in there, we're going to call that the rotational inertia. So what we created here is kind of like Newton's second law, but for rotational stuff instead of linear stuff. Instead of just pushing things in a straight line, this is kind of like for rotating things. If you apply a torque, then it will create an angular acceleration. But it's dependent on two things. It's not just dependent on the mass, but it's also dependent on where the mass is. So this is going back to our door analogy. It depends on where you push on the door, right? That depends on how easy it is to open the door, or how much the door rotates. If you push really close to the hinges, the door doesn't rotate very much, right? But if you push out close to the handle, it rotates much more for the same amount of force, right? That's where the R comes in. That's why the R is important. So the mass of the door is important, but the R is actually more important. Why? Because it's squared, right? My favorite example of this idea is I grew up in Livermore, California, where there is this neutron shield door, as it is called. And this is what it looks like. That's a really old picture, man. That's like early 80s. You can tell by her clothing. But this neutron shield door is actually still here, still there in my hometown of Livermore. And it has to be super thick because there's high energy neutrons inside this building that if they get outside this building are very dangerous to humans. And so they make this huge door so they can go in and out. This door can be opened by a single person. It is intensely massive. I mean, extremely massive. And lots of parts of it are made of lead. In fact, on the back side of this door, it's kind of funny. See if they show the back side of it. They're not really showing the inside of the door. But the inside of the door just has one of those like bars on there you push to open a door. It just has one of those sitting on it. It's kind of funny. You push this thing and then you push open this 25-ton door. And so anyway, this the reason that you can do this is because you have this huge distance out to here to apply a force. This distance here is, I want to say like 20 feet or something like that. It's a wide door. So you have a huge R, excuse me, you have a huge R in here. You still have a big mass, but the huge R is squared. So that gives you even more torque, essentially. Your torque is quite large. It doesn't mean you're going to be able to open the door really easily. It's not going to just fly open and bang against the wall like some doors do. It's going to be a very small acceleration here, but you can get enough torque to open that with one person pretty easily. And that's true of most doors. How many of you have you ever taken a door off of the hinges in your house? Do you have solid doors or hollow doors? Hollow. Anybody have solid doors? Solid doors are pretty rare inside of most houses, but if you have solid doors, I have some solid doors that I'm going to put in my house. I actually have a couple of solid doors in my house, actually in the older part of my house too. But I'm going to be putting in these solid oak doors. Holy crap, they're heavy. But once they're in, you can't even tell. Because, you have this nice distance. I mean, they feel definitely heavier than hollow doors. But it's not much of a big deal because the distance matters more than the mass because it's squared. This mr squared thing, we're going to call the rotational inertia. What that means is it tells us how much something wants to rotate or doesn't want to rotate. If it's a bigger thing, a bigger number, it wants to rotate less. Bigger numbers are like bigger masses, and bigger masses want to accelerate less, right? Bigger things with bigger rotational inertias want to rotate less. And it's not always m times r squared. That's only for something like a ball on the end of a string, a point at the end of a distance r. If it's a different shape, it actually changes it entirely. It changes what the rotational inertia is. So here are some, we don't do these calculations in this class because it's calculus. It's required to do it. But here we actually show you the different rotational inertias for different shapes in different situations. So here is a hoop or a ring that's rotating around the center of the ring. That's mr squared, just like we just did. The rotational inertia of a ring is just the mass of the ring times the radius of the ring squared. However, if it's a solid cylinder, so it's like a quarter or a solid cylinder or disc, it's mr squared over 2. So which one of these is harder to spin? The ring or the disc? Which one is harder to make it spin? If they have the same mass and the same radius, which one will be harder to spin? You say the cylinder will be harder to spin? Why? It actually does have a shorter distance to its mass, but let's say the R's are the same. Let's say the radius is the same. What if this disc was the same radius as this, but this one had all of its mass on the outside ring, and this one has its mass distributed from the inside towards the outside? Which one do you think would be easier to rotate. I happen to have somewhere I have to remember. I used to have no, I have it somewhere. There's sort of rearranging things, so now I'm really lost. I'll be even more lost than I normally am for the entire next year, I'm sure. Oh, let's see here. Luckily for us, I bought some new ones. I just had to find them. So here is a ring and a disc. They're about the same mass and the same radius. We're going to have a race. So which one do you think is going to win? Make your predictions. Which one's going to win? Wood or metal? Make your prediction. Everybody's got to vote. Wood? Okay, vote for wood. Metal, metal. So why do you think the wood one will win for this one? Actually has the same mass.
Oh,
Yeah, same mass. This one just has its mass spread throughout the whole thing. This one has all its mass concentrated out here. Right? Remember, it matters where the mass is. Remember, the door, when you push on it in the center, it's much harder to move it than if you push it on the outside. Right? So this is kind of related to this. Well, let's just raise it. So the wood one, why is that? Let's think of it in terms of our door here. Our door has its mass spread throughout the whole thing, right? What if we had the door, what if we made the door way thicker on this end, made it really, really thick on this? What if we hung a bunch of weights out here or something? Would that change how hard it was to open this? It actually would. It would change how, because I'd have to move all those weights. And if I was pushing it from here, it would definitely make it harder. If I pulled it from here, it would make it harder. You know, if somebody comes over here and hangs on this doorknob, we're not allowed to do that, but if you hang on this doorknob, it will make it harder to close. For sure. However, if you come and hang right here, it hardly changes anything at all. Why? because this one is closer, if I'm hanging here close to the pivot point, it doesn't require much force to move things that are close to the pivot point. Right? When things are close to the pivot point, there's just that small distance, no big deal. Right? But that long distance it's hard to get that thing moving. It's hard to, if you add mass to the outside, it's hard to get it going. Here's another example. We got, here's one you can do right at the table. Let's see, we need something heavy. Okay. So now, you're going to have a tug of war with this thing, but you can only move it. You can only hold it. You can only hold these things by the ends. You guys can only hold by the ends. You want to hold from here, you're in the tug of war, right? And you're going to try to, you guys are going to try to get your, you're going to try to get it to his computer. You two are going to try to push it down, okay? Your job is to push it this way, and you can hold it anywhere you want. Okay? Oops, you need this too. Okay? Now, you guys probably don't want to go opposite ways because you're both trying to push it this way. You probably want to get yours on this side. You're both going to push this way. She's going to push it this way. Okay, ready, go. Right, she can hold it even now. You can hold it closer. You can try right up there. And move away, right? Pushing from a long distance on something, if you have a long distance away, it's hard. You're having to push really hard and not getting much of the same. Right? She doesn't have to push hard at all. She's got that short little distance. It seems a little counterintuitive, but it's very true. Now here's an application of this. Let's see. So, NASCAR racing wheels are designed specifically, in fact, all racing wheels are designed specifically to, see if I can find a really good example one. There's a real one right there. NASCAR racing wheels are designed specifically to limit the amount of weight out on the outside edge of the wheel. Because you don't want to have all your weight on the outside. If you have all your weight on the outside, you're the ringman, you're going to lose. Every time you come out of the pit, it's going to be harder for you to get your wheels going, right? So you want to minimize the amount of weight on the outside, and you want any weight that has to be there, you want it to be as close to the center of the wheel as possible, because that's easy to move, right? So notice how close these things are, all these lug nuts are to the center of the wheel. Extremely close. Now on a NASCAR car, you have to have 5 bolt wheels, I think. So your wheels have to have 5 lug nuts on them, essentially. So hence this, you've got these things super close in. You've got holes in the wheel, right? You've got all these holes in the wheel. I don't know what these wheels can be made of. I don't know if they can be made of aluminum or carbon fiber or whatever else, but guarantee you they're made of the lightest material that they're allowed to make them of. There's a lot of rules in NASCAR, right? And this is not done by accident. This is done by science. They're using science to make this wheel the best possible wheel they can. If you go into, if you look at, the wheels that people put on their cars, it's a very similar design. These bolts are very close in. The weight here, this is a solid part, but everything as you go further and further out, there's less and less solid wheel, right? And another thing that they do a lot of times on these wheels is they make a very, very skinny tire with a very, very lightweight rim. This is a little bit of an advantage, a little bit of a disadvantage. The tire itself is very, very heavy, oftentimes much heavier than the rim itself is. And so sometimes that's an advantage. Sometimes it's a disadvantage though. So it just kind of depends. Like when you're in a racing, if you were actually racing this car, this wouldn't be great because you can't have a very thick tread on this. That means you can't go as many laps, right? So if you're this would be no good for NASCAR because you couldn't put a very thick tread on it. You lose tread quickly and can't afford to that. But let's look at Formula One. Formula One racing wheels are quite different. Here we go. There's a Formula One wheel. There's no bolts in it. That's because there's only one single bolt right in the center of the wheel. Right where it won't matter at all. Even an inch away from that, and a Formula One car won't perform as well. So they have one right in the middle, right in the middle, and that's it. I love their steering wheels too. Aren't those cool? How'd you like to have a car with a steering wheel like that? So Formula One is not about it's not about rules. It's just about winning. There's hardly any rules in there. But you can see right here that it's got a single bolt right in the center, and that thing comes out just boom, once out, and you change the tires. You're done. So very, very efficient. Also, they can make their wheels out of just about anything they want. So they'll have wheels made of magnesium or whatever, carbon fiber. I think Ferrari is using carbon fiber now. Same thing goes for bicycle wheels. Bicycle wheels are designed very much this way. As little weight as possible on the outside edge, as much weight as possible towards the inside if you can do it, and then you have the least amount of problems with that. I got to know what Koenigsegg has on theirs. I can't remember what their wheels like. So Koenigsegg makes the fastest car on the planet, pretty much. That's the production car that you can actually buy. That's their latest one. Yeah, their wheels look very similar. Man, those are low weight. Those are all carbon fiber wheels. Single bolt right in the center. I think they've gone 320 miles an hour. Or something like that. That's just insane. How do you go so stinking fast? All right, so which one of these shapes do you think has, so let's go back to the hoop in our solid cylinder, our disc, right? Hoop and disc. The hoop, if it has the same M and the same R as the disc, M and R, that means the disc had half of the rotational inertia as the disc. And half of the rotational inertia means it was easier to get going. The smaller the number, the easier it is to get it rolling. So which one up here has the smallest rotational inertia if the mass and the radius is the same? Don't consider this one. Because it doesn't have a radius. Which one has this? Which one has the easiest time getting rolling or spinning or whatever? For all the ones that have radiuses, I mean, which one? What makes it easier to spin? What about this number makes it easiest to spin? Bigger or smaller? That's essentially what we're asking. Bigger number is harder to spin. Smaller number is easier to spin, right? So which one's the smallest? So 2/3 is bigger than 1/2. 2/5 is smaller than 1/2. I think for all the ones that have a radius involved, this is it right here. Like some of them don't have radius, that doesn't have a radius, that one doesn't have a radius. So if we have a ball that's the same radius as that disc, and it's the same mass as that disc and that ring, then it would actually win the race between the three of them. Now I need to find a ball the same size, the same mass, same radius, same mass. But notice we have other things here. Like this is a rod that's spinning around its center axis, so that's like a rod that's spinning like this. Get it to spin. Yeah. It's a rod that's spinning this way. Like this. Right? That's this one right here. This one's a rod that's spinning around this end, so it's going around like that, right? This one is, so this one's for a thin rod, this is for a thicker rod, or a cylinder or disc that's spinning around this axis. This is for a thick ring, this one's for a thin ring, this one's for a thick ring that has an inner radius and an outer radius that are much different. That's quite a bit different. Here's a shell of a spherical shell, like a ball that's hollow. So every one of these has a different rotational inertia, and that rotational inertia will tell you how easily it wants to spin or how difficult it is to make it spin. In other words, how much torque it takes to make it spin. So let's talk about how we use this moment of, they call it a moment of inertia or rotational inertia. So we have a person that's pushing a playground toy or this merry-go-round thing, and he's pushing it on the edge, which means he's applying a torque. There's the force, and the distance is the radius of the merry-go-round, and it's a 90-degree angle, so it's just force times R, and that'll be the torque, and the force is 250 newtons, and it's 1.5 meter radius, so that's how we calculate our torque. And the angular acceleration that's produced is going to come from the equation torque equals I times alpha, where I is the rotational inertia of this thing. We're going to pretend that the merry-go-round is like a disc, like this one, that's going around its center axis. So its I will equal the mass of the merry-go-round times the radius of the merry-go-round squared divided by 2. So we calculate I first. No, they calculate torque first. So they're calculating torque first. The torque that he's applying is R times F times sine of theta, 375 newton meters. The moment of inertia is 1/2 mr squared. So the mass of it is 50 kilograms. The radius is 1.5 meters. They calculate I to be 56.25 kilogram meters squared. Then they plug this I and this torque into the equation into the Newton's second law, quote unquote, for rotation, which is acceleration equals torque over I, or torque equals I times alpha. Either way, we do it this way so we can solve for the rotational acceleration. We're able to calculate that. Now, what if we put a child on the merry-go-round? What if we put a child on here somewhere? Now, a child on the merry-go-round is like putting a ball on the merry-go-round. It's kind of like this guy. It's like the ball on the end of a string going around and around. It's like putting a mass in one spot. Rotational inertia for a mass in one spot is this one right here, mr squared, which happens to be the same as this one for a hoop. So if you just add a mass somewhere onto a rotating object, you use this one for each mass. And if you're doing two objects that are rotating, it's just like two masses that are accelerating. You add them together. But in linear stuff, we added the masses together. In rotational stuff, we add the rotational inertias together. So if we're going to have a child and a merry-go-round going around, then we have to calculate the rotational inertia of the child, which is mr squared. They calculate that here. Their distance of the child from the center of the merry-go-round squared times the mass of the child. And then they add that to the rotational inertia of the merry-go-round, which was the 56.25. Rotational inertia of child, rotational inertia of merry-go-round. Total rotational inertia, I, is 84.38 kilogram meters squared. Then they plug it into this equation again to calculate the acceleration. Now, what would we expect this to be? When the child gets on, is it going to accelerate less when the father pushes or more? So the father pushes the merry-go-round and accelerates it whatever it does, then stops it, puts the child on, and pushes again with the same force. Is it going to rotate less or more with the child on? Less. Why? More mass. More mass you pile on, the harder it is to get it going, which means it's going to accelerate less, right? And it does. Here it is, 4.44 radians per second squared. The original was 6.67 radians per second squared. So it does rotate, it does accelerate less. So that is Newton's second law with rotation, or in other words, the dynamics of rotational motion. You have rotational inertia, which takes the place of mass. We have an equation, torque equals rotational inertia times acceleration. Instead of mass, we have I. Instead of A, we have alpha. Instead of force, we have tau. But it's still Newton's second law. Right? Where the rotational inertia is dependent on the shape and how it's rotating. If it's rotating around the center axis, or if it's rotating around one end, like in this case, it's rotating around one end, or maybe it's rotating, where the loop is spinning, like I'd spin my ring on the table, but my ring is 3 rings, it doesn't spin very well. So it depends on essentially where the mass is and how it's rotating. And I think that's where we'll leave it at. We'll come back to chapter 10 on Wednesday, finish it up, talk about kinetic energy, angular momentum, and collisions, and gyroscopic effects. Actually, you know what? Let's do rotational kinetic energy really quick. It's actually not that hard. So. Rotational kinetic energy is really simple. They're going to do a calculation of it here, but in the end, it's really quite simple. 1/2 mv squared was kinetic energy for linear. Instead of m, we use I. Instead of v, we use omega. It's 1/2 I omega squared for any rotating object. Now, what does this mean? This means that if you're rolling down a hill, let's see if they have an example of it here. Remember we did the cars on the ramps rolling down, and we did conservation of energy? Your numbers weren't really that great, were they? No. And that's because some of the energy so you had potential energy at the top of the hill, you had kinetic energy at the bottom of the hill, but some of the energy wasn't accounted for. You had 4 wheels that were rolling, that were spinning, and 4 axles that were spinning. Each one of those wheels, or 2 axles that were spinning, but each one of those wheels and each one of those axles has some kinetic energy that came from the potential energy at the top of the hill. And we never accounted for it. So, potential energy at the top of the hill equals kinetic energy of the car moving, but also kinetic energy of the wheels rolling. Each wheel had a kinetic energy of 1/2 I omega squared. So it'd be 4 times 1/2 I omega squared for all the wheels. And then each axle would have a rotational kinetic energy of 1/2 I omega squared. You'd multiply by 2 to get each axle. So there's extra energy we never accounted for. And if we added all those in, your beginning numbers and your ending numbers would have been a little bit closer. Because I'm guessing your beginning numbers were bigger than your ending numbers, because that's what it usually ends up as. But that's your rotational kinetic energy. So essentially you have to add that in. It can be used to do all kinds of things. In fact, they've made many cars and other vehicles like this, where you start a big wheel spinning inside the car, and then you use that wheel to drive the wheels of the car, right? And that's called a flywheel car, a flywheel-driven car. But we actually have them in our engines today. Our engines are designed with these big, heavy wheels inside of them, called flywheels, to help keep the engine running when you stop at an intersection somewhere, right? So that you don't have to use your battery to keep your engine running all the time. So these flywheels are spinning on the engine all the time, and if they're kind of designed so that they keep the compression going inside the engine, big heavy wheels. So here they actually calculate the energy to stop a grindstone or to start a grindstone. It's still kinetic energy is still equal to the work done, but work is now torque times angle instead of force times distance. So work can be torque times angle, and it'll give you the same amount, same thing. So they do an example of torque and angle. Here they talk about helicopter energy, the energy in a helicopter blade, right? 1/2 I omega squared, where a helicopter blade, the I kind of looks like a stick rotating around its end. So you have to go back to the previous chapter and see how to calculate I for the helicopter blade. The helicopter blade, you would use this shape right here, would be like the helicopter blade. So it's the mass of the blade times the length squared divided by 3, and that would be for each blade going around, would be the I for those blades. So that's not terribly difficult. We have another kinetic energy to add into the equation. Like we had several potential energies, we have another kinetic energy when we do conservation energy now. So that is all we'll do for today. I hope you have a good evening. We will meet again tomorrow to do lab and answer any questions on chapter 9, and then we'll start chapter 10 homework and answer questions of chapter 10 on Wednesday. We will see you later.